All right, so we'll start this up from scratch so that you can see that the default values do in fact open up, that the outputs are all zero, so that tells you that they're not default, that this isn't just a ran program. These are actual, I had to go in and set these as default. You can see you got your ones here for your circuit elements and just kind of like how the homework has it laid out. It's very similar. They're all well labeled and documented as to what you're looking at. Same thing with the outputs. I'll move my head there. You can see got our 9 outputs pretty well organized. Here's our block diagram. I know it's looks like a bit of a mess, but I assure you this was very easy to create. It didn't take very long, and really the problem didn't take very long either by hand, as you'll see in my report. I The strategy also described in the report, but I'll briefly go over, is that if you go and look here at VA, this was the very first thing I did was calculated VA. Now there's a lot to VA because that is, it's knowing what your currents are, and then moving all your coefficients to one side, and then there's a big division that takes place that produces VA, and that's why I called this division VA, because you had to sum up all your terms that were had VA in common, and then sum up all your terms that didn't have VA in them, and then VA times all of the terms that they have in common equal to the ones not in common. Then you just divide, and that gives you VA. Once you find VA, it's really you've already like done the hard part. The rest of it, you just go back to you actually backtrack to your hand calculations of, for example, I1 was 10 angle 0 degrees minus VA over 1 plus J4. So you just take those values and you build I1 using this difference, and then you divide it by that sum. The only challenge I really ran into that was different from hand calculations is that LabVIEW apparently works in radians when it does computations. So if you're going to have a user specify a phase shift of any kind, you need to convert it to radians. And quite frankly, I just thought this was the easiest way. You see the constants here, and that's the conversion factor. And then you just invert it to convert it back to degrees. I'll do it up so you can see. Um, we'll run it. These values are basically the same thing that I had. Um, little variation. Yeah, little variation. Um, I think the largest difference in these values was 0.02, as you'll see in the report, which adds up to less than 0.3% error. So that's pretty close. Um, I guess that's about it. The only other design um, the only other design feature that I have to mention are these complex command blocks. You can see the one I have my mouse on right now is converting our rectangular complex value into polar form, which makes it very easy to display them to our indicators. I'll show you real quick. Yeah, this is where they've been split, and then they just go to their indicators, and there's little operations that take place on them. Um, I guess other than that, then you have these right here where you just have to use some intuition. I think you have to recognize that your real part, of course, is always going to be your resistance, and then your imaginary part is your frequency times um your inductance, and then for capacitance, of course, it's the reciprocal. The other thing I had to run into is I had to add a constant -1 because of 1 over J is not really recognized as negative J in LabVIEW, so you have to make sure that you specify this is what makes it the reciprocal. or I mean, is what makes it negative J um, equal to 1 over J is by multiplying this by -1, then doing the reciprocal. After that, to find power, uh, it's just current times the voltage of the across the resistor. You could have, I guess I could have hard coded it to say since they were all one, but I wanted to make sure that if you change R1 or R2 or R3, that you're going to get the right value and then it's not just hard coded for one. So what you have here is you have uh we can see right here. So you have I1 times R1, so that's the voltage, and that's just I squared times R. That's current. That's a power right there, and it's only the real part. You don't use the phase angle because we're just talking about resistors. And that's it.